Okay, hi everyone. My name is Chi and welcome to our very first KL Mini Hack workshop series. Today we will have two speakers, WeiHan and Kevin. WeiHan will talk about Unlearn, a very interesting topic which I personally feel, Unlearn and Relearn Ethereum basics. And Kevin is going to talk about another very important topic in the ecosystem, which is the clients of Ethereum. And he'll probably go through on how to set up with a tool called Sedge. So these two are very interesting topics. So hope you'll enjoy. And without further ado, I will let WeiHan introduce himself and let him to take it away. WeiHan, do share your screen.
All right, so let me share my screen. Okay, can see?
Yep, it's working.
All right, cool. Then I think I can just start right away. So before that, let me just introduce myself. My name is WeiHan. Currently working as a blockchain engineer at a company called NodeReal. So I just joined as one of the core contributors or core dev for BNB chain. So yeah, very excited. I mean, just joined like 1 month ago. So, and I'm a fresh grad, so I'm not an expert here. I think some of you are definitely more expert than me. But nonetheless, let's talk about the session today. The topic is called Unlearn and Relearn, nothing fancy. It's all about Ethereum basics. And why do I say Unlearn and Relearn is because I'm pretty sure some of you here have been in the Ethereum ecosystem for quite some time, and some of you are not, right? So for those who are already an expert, I hope this session is still going to be valuable, even though we are talking about basics, by helping you to unlearn and relearn so that you can fill up some certain knowledge gap that you didn't know that you didn't know, right? And definitely for beginners here, it will be a great starting point for you to step into the Ethereum ecosystem and also to know about what's going on behind the scenes of the Ethereum blockchain as a whole. All right, so yeah, without further ado, let's start off with some meme. Yep. So if you are into the crypto market or if you own some Ethereum or some other cryptos, you probably don't feel that well, I guess, unless you are very good at predicting the market. But yeah, nonetheless, we're not going to talk about the market today. We're just going to talk about the technical side, right? Because we are all builders here, right? Or we are all going to become a builder here. So what we're going to talk about in this session is more about the technical perspective of Ethereum. So this is a MetaMask transaction. So for those who don't know what is MetaMask, MetaMask is basically a very well-known platform or very well-known wallet for people to make transactions, right? So if you look at the picture here, what I'm trying to do is just very simple. I'm sending 0.2 ETH, or in this case, it's testnet ETH from account 2 to account 1. So it looks very simple and it feels very simple as a user, but there's a lot of things that's going on behind the scenes of by pressing this very simple button, and we are going to explore all of that. So let's start off with one section. Wait, let me just open the comment section. View doors. Okay, yeah. So let's start with some blockchain basics, right? And yeah, again, it's just going to be a very basic thing. So first off, state machine. Okay, so if I were to summarize what is Ethereum, I can summarize Ethereum as a state machine. So, and to be more specific, Ethereum is a transaction-based state machine. So you might ask, what is a state machine? Okay, let's talk about the word state. State is nothing more than, if you are from computer science or any technical background, it's basically just like a database. You can think of it as a database. A state is like a database that stores certain data or that stores certain persistent data. And the term world state means that this world state is like a universal state, or like a state that is consistent throughout the entire Ethereum ecosystem or the Ethereum network. That's why we call it as a world state. And you can see there's an arrow here that's transit from the first world state to the second world state. So in order to transition from one form of world state or one form of database to another form of database, you have transaction to facilitate this change, right? So to give more concrete example, right? So let's say in this world state, like what I said, it's just a database or it's just stored certain data. Let's say in this data, in this state or in this database, it says that Vitalik has 10 ETH and Elon Musk has 5 ETH. So you will send a transaction such that the sender is Vitalik and the recipient is Elon Musk and the amount is 2 ETH. So after this transaction is successful, you will have a latest version of world state that states that, okay, Vitalik now has 8 ETH and Elon Musk now has 7 ETH, right? So as simple as that, this is literally it for Ethereum as a blockchain, right? It's just the change of state. So when people say that, oh, I own 1000 ETH, it's nothing more than just saying that, okay, in this Ethereum state, in this Ethereum world state, I own 1000 ETH, right? So you don't physically own the assets, but you own the asset by referencing to the state, right? Okay, talk a lot about world state, and let's continue to the second one. So if you think about transaction, if you think about Ethereum as a transaction-based state machine, that means that every time you send a transaction, you update the world state. But does it make sense for you to keep updating the world state from one to another, right? Like after one transaction, you will have a second world state, another transaction, third world state, right? Only one transaction. I mean, one world state is facilitated by only one single transaction. It's not efficient because when you update the world state, it will take some computational cost. Computational cost means money. So instead of just one single transaction, we bundle them into a block, right? So a block here is nothing more than just a package of transactions. It could be a lot of transactions as a block, right? So what it means here is that, okay, for the first world state, to go to the second world state, it will run all the computation from these transactions here, right? After running all of these transactions, then you have a finalized state. Then this will become the latest world state, right? So a block is just a package of transactions. So now if we connect everything together, you have something like this, right? Because like what I said, you have multiple world state at some time, right? So if we have a chain of world state, something like this is followed by a chain of blocks. So Ethereum is nothing more than just a chain of states facilitated by a chain of blocks, and hence the word blockchain, right? So nothing fancy, right? So this is the high level overview of blockchain, right, as a whole. Now they understand the overview of what's going on behind the, in terms of the high level side, let's explore a little bit about each component. And the first thing that we're going to explore is world state. What's inside the world state, right? So inside the world state, we have something called accounts, right? So accounts, if you have your bank accounts, what does your bank account do? Your bank account basically holds some money, right? So it's the same, or it's almost the same. So in this case, a world state holds a bunch of accounts. And if you look at what are those accounts, accounts are basically mapping of address and account state, right? So for those who have interacted with MetaMask or other forms of wallets, or at least you have sent a transaction before, you have something called like a public address or certain address. So it's similar here, where you have when you own certain account, that means that you own the address that links to a account state, right? And the follow-up question that you guys might have is, okay, now that I know what is account, I know what is world state, what is account state? What is this thing here? What is inside the account state? So inside the account state, there are 4 things. First one is nonce, second one is balance, third is storage hash, and the fourth is code hash, right? This is where things become a little bit technical, slightly more technical. Okay, let's start with nonce. So nonce is basically a counter. Counter means that it can only increment, it cannot decrement. 1, 2, 3, 4, 5, 6, 7, right? So nonce is basically included in this account state as a form of mechanism that can prevent double spending. So what is double spending? I think you can Google it yourself. But the point here is that it doesn't allow people to spend their token multiple times at once, right? Hence you have this nonce variable, right? So if you want to know more about what does nonce do in more details, definitely you can check it out. But to summarize, nonce is a counter variable or a counter that can help to prevent double spending. Secondly, you have the normal property called balance, right? So a balance basically states that, okay, this particular account holds how many ETH or how many Ethereum, right? And the third one is storage hash. To summarize, it's just a hash of a certain account storage. But if you want to go deeper, I can take probably around 1 to 2 hours to explain the mechanism behind account storage, because it's another huge topic. But you can just think of it as a reference to your account storage. And what we mean by account storage here, everything here is bytes, right? Or very low level, bytes lah, basically. And code hash is the same thing as well. It basically stores the code that you can use it to execute certain computation, right? So 4 things: nonce, balance, storage hash, and code hash. Now that you understand what is account as a whole, right? Let's explore what are the types of accounts. Typically, there are 2 types of accounts. Not typically, it's actually And yeah, actually, there are two types of account. The first account is called externally owned account, EOA. The second one is called contract accounts, CA, basically your smart contracts. So if you look at the visualization here, you can see that I put this as a, I think, darker color. It means that it technically doesn't exist on, technically means that, for EOA, storage hash and code hash, technically doesn't exist on account state. Okay, I can't say that it technically doesn't exist. It exists on account state, but it's just empty value. So basically, it doesn't have any use for EOA. So you can think of this as EOA only have two main properties. One for account state, one is nonce and one is balance. So it's just a simple bank account, right? That literally just states, okay, what is your balance of this account, right? So this is EOA. And EOA, most importantly, EOA is controlled by a private key. So again, for those who have interacted with MetaMask before, you will know that if you set up a new account or new wallet, you will need to you ask you to save your seed phrase or your private phrase or your private key or things like that. Because if anyone have access to your private key, they will have access to your account and they can do whatever that they want with that account, right? So that's EOA. And the second account is called contract account. It's basically your typical smart contract account. So this smart contract account would have everything that we stated just now. We have nonce, balance, storage hash, and code hash. And most importantly here, contract account is controlled by EVM code, right? So to put it more precisely, a contract account cannot initiate transaction. A transaction can only be initiated by an EOA, and that transaction can do a message call on a contract account, and once you call the contract account, you execute the code stated by the contract account, do some computation, then update all the storage hash, storage data, and so on and so forth. Maybe I'll talk more about it later when I talk about transaction. But these are the type of accounts that exist on Ethereum: EOA and contract account. Account abstraction is getting rid of the need of EOA. I'm glad you asked, because I'm also going to talk about account abstraction in the upcoming few days. But to answer your question, the goal of account abstraction in the future is trying to eliminate EOA. That's the vision. But in the short term, it's very hard, because when you say eliminate EOA, you're eliminating the first class citizen in the entire ecosystem. That means that you need to make a lot of protocol changes in order to make it happen. We'll talk more about account abstraction in the future, but that's the goal that we have. But it's hard to do it. Yeah. What are the differences between seed phrases and private key? Seed phrases is just it's just a more convenient way for people to store their private key. I'm not 100% sure how do you generate seed phrases, even though I Googled it just now. But there is a way that you can generate seed phrases such that it will become words, right, that people can understand. Because imagine that you have to store your private key. It's like very weird looking, right? 6E, 1, 2, 3. It doesn't have any meaning. So if you were to write it down on the paper, it's very hard for people to, maybe may miss one digit or may miss one character. So it's not very user friendly. By having a seed phrase, it's less likely for people to make any mistake. And hence, that's why I think people or people in the ecosystem wants to go with seed phrases instead of just the normal hexadecimal that you have from the private key or other places. Yeah, that's my understanding, but definitely correct me if I'm wrong. I'm not the expert here. I'm just sharing my knowledge. Okay, let's continue. Thanks for the question, by the way. So quick recap. We have talked about a few things. We have talked about world state. We have talked about an account. So a world state is basically contains a bunch of accounts. What is an account? An account is a mapping of address to an account state. What is inside an account state is nonce, balance, storage hash, and code hash. Right. So you have this world state. It can go to another form of world state by executing blocks of transaction. Right. So this is literally the blockchain basics. No, not yet. We are going to explore the next one, which is transaction. Right. So what's a transaction? Right. If you look at from an Ethereum point of view, a transaction is basically an instruction signed by an external actor holding a private key to an account. Right. So that means that you as a user, you have your own private key. When we say that you have your own private key, that means that you have access to an account in the world state. That means you can submit a transaction such that you can modify the world state. Or to be more precise, you're modifying the account that exists in the world state, right? So that's it for transaction. And there are typically two types of transactions. The first transaction is called contract creation, and the second transaction is called message call. The first type, which is contract creation, basically means that you are submitting a transaction to create a contract, right? To create a contract means that you are modifying the world state such that the world state right now has a new contract account, right? And the second type is called message call, which is basically the same thing. You are modifying the world state such that your account, your EOA account, can message an EOA, another EOA, or another contract account. And notice here why I didn't put CA here, right? And the answer is because, like what I said just now, transaction must be initiated by an EOA, right? And that EOA will give a message call to an EOA or to another CA. So no matter what, if you want to initialize your contract account to do something, you must always start with EOA. And when we talk about account abstraction, then we will know that why is this bad, right? Or why is this not efficient enough, right? So, but we're just going to leave it as this for now. So to summarize, there are two types of transactions: contract creation and message call. And to look deeper into contract creation in terms of the world state point of view, if a world state, let's say previous world state is like address 1, 2, and so on and so forth, and in the second world state, or in the newest state, you will have a new address, right? So as simple as that, it creates a new mapping. And for message call, so previously you have an address and account state, right? And remember, account state contains storage hash and code hash. So let's say once you initiated the transaction, in terms of the message call, you would update your storage, right? So to put it simply, a contract creation basically creates a new contract account, and a message call basically updates an account. Yeah, that's all, right? One is update, another one is create. Yeah, and yeah, that's it for types of transactions. And the next one, okay, EVM, Ethereum Virtual Machine. So to be very honest, I am not 100% expert in EVM, and it will probably also take me 3 hours to explain what's going on underneath EVM, because it's a very hard topic actually, and so I can't cover everything, but I'll attempt to give an overview of what's going on on what is EVM, right? So, but yeah, it will be quite brief. So EVM here, previously we mentioned that you submit a transaction. It can be a message call, it can also be a contract creation, and then you will modify the world state to become a newer state. This should be S2, my bad. But how do you execute all these transactions, or how do you perform all these codes, right, or code functions? And the answer here is by EVM, right? So looking at this diagram here, looks kind of messy. Basically, it's taking the storage of the account, code of the account. You're taking the input data of the transaction. You perform all the computation, then you update the storage, right? So this is what an EVM does, right? So, So if you look at the architecture of EVM, you look something like this. You have a virtual read-only memory. So read-only memory, this one stores, if I'm not mistaken, it stores the call data's input data, meaning the input data, if I'm not mistaken. And it will have a second component called machine state, and the third component, which is the storage, right? So in the machine state, this is where the exciting things that will happen. So you have a program counter, you have gas, stack, and memory. So for those who are familiar with assembly languages and assembly languages or low-level languages, especially for those who are in computer science or software engineering, then you would feel familiar with this architecture, because it's very similar to our normal computer architecture that you have right now in your laptop or in your desktop, right? So yeah, but again, it's very complicated, and I tried to simplify and try to summarize, but I couldn't. So I'll just leave it at this for now. Maybe I'll try the next few slides, I'll try to summarize what's going on with EVM. But yeah, let's skip this first because it's very hard. So there's something that is also important in Ethereum. It's called gas, right? So before I talk about what's going on here in the slide, let me just talk about why do you need gas? Like people always talk about gas fee. So let's imagine a scenario where you don't have gas, right, in the Ethereum blockchain. So if you don't have any gas, that means that anyone can spam call the network. That means that anyone can spam transactions on the network. When you have a spam, like let's say 1 million of transactions sent in just a one second, you would clog out the network. That means that the network will become slower, or you freeze the network, right? In computer science term, it's called denial of service, right? Or DOS. So to prevent that from happening, we have a concept called gas. Gas is basically a transaction fee, right? So previously, let's say if you don't have any gas, attackers can spam call the transaction, spam the transaction because they have no consequences of doing the spamming. But with the introduction of a transaction fee or gas, in order for people to spam the network, they will have to spend money, because every time they make a transaction, it will cost some transaction fee. So if they want to spend 1 million times, they have to spend, like, let's say 1 million, maybe let's say 1 million USD, I don't know, depending on the price of ETH. So it's not feasible for the attackers to do. So hence, this is why gas is very useful to prevent like spamming attacks, right? So now that I understand why do we need gas, let's talk about this new gas mechanism. So you can see here following EIP 51559. Okay, so for those who don't know what is EIP, EIP stands for Ethereum Improvement Proposal. So it's basically like what it says, it's a proposal. So that means that every time a community wants to improve the protocol, they will submit a proposal and say that, okay, hey, I feel like this architecture is better for the Ethereum network. What do you guys think? Then people will discuss and they will, they will see if this proposal is valid. If let's say it's valid, then they'll implement this proposal in the protocol, and then hopefully it will make the protocol become better. Right, so that is what EIP is, right? And 15559 here is basically a very special code for this particular proposal, right? It doesn't have any meaning, and yeah, it's for you guys to memorize if you guys want to memorize. But yeah, this is basically EIP. So in this proposal, I think published, like I forgot which year, but basically there are a few types of new gas fields, and the first gas field is called base fee. It's determined by the network and is subsequently burned, right? So when we say burn gas fee, right? I think one thing that it might come to your mind is deflation. I'm not 100% sure is Ethereum is inflationary or deflationary, but if you were to burn gas, or if you were to burn ETH or burn money from the entire supply, you are basically reducing the supply of the money in the circulation. So if you reduce the supply, just economy, the price of the value of the money will increase, right? So that's why it's deflation. But yeah, I remember it's quite complicated for Ethereum, whether it's deflationary or inflationary. But just now I checked, it's deflationary because of the burning of gas fee. But I think it's more complicated than that. But let me just put it as this for now. So that's base fee, right? You burn this base fee of gas. And the next one is called max priority fee. So max priority fee is like a tip fee. You are basically paying the validator directly so that they can prioritize your transaction, right? It's like a tip, right? If you want your validator to prioritize the transaction, to make your transaction faster, then you pay them more, right? And the third one is called max fee per gas. Basically, it's the maximum gas fee that you are willing to pay, right? Because you wouldn't want to spend all your money on just paying on the gas fee. So there's a limit that you want to set, such that if it exceeds the maximum fee that you set, then you don't want to perform this transaction. Yeah. So these are the things that that's happening in the gas section, right? So yep. Okay, next one. Just the summary of EVM, like what I promised just now, right? There's a lot of things happening behind EVM. Literally a lot of things happening. I think I spent like 3 days trying to understand. But to summarize, you will write a certain smart contract, right? You can write a smart contract in certain languages like Solidity. This is the most famous one, or like I think Viper or other languages. Once you have written this smart contract code, it's compiled into bytecodes, and this bytecode can be read and interpreted and executed by EVM. So when we say executed by EVM, that means that it's performing some sort of transaction, some sort of computation, and then it will modify the world state, right? So this is the summary of EVM, right? But again, if you guys are interested into knowing what's going on underneath all these things, I can send you a few links and hopefully you won't suffer. Yeah. So next, it was evolutionary, now it's deflationary. Yeah. Thanks, Nicholas. I remember, I mean, from hindsight, yes, but I think someone did some calculation that states that it's not just so straightforward. But yeah, okay, we'll discuss it about it maybe next time. Okay, let's not make it complicated because this is Ethereum basics. All right, next, consensus, right? So again, consensus is also something that I can take 3 hours to explain everything, but I have very limited time, so I'm just going to explain a very high level overview of what is proof of stake. And for those who are interested in the history of Ethereum, previously it was proof of work, now it's proof of stake, right? Because of the merge, which happened like few months ago. So yeah, now we have proof of stake as a consensus algorithm. So this is how it works on a very high level overview. It might not be 100% accurate, but this is the overview. So anyone can become a validator, right? So in order to become a validator, you basically stake 32 ETH into a special smart contract. So once you stake that 32 ETH, you will become a validator, right? So what does validator do? Is basically you have a certain privilege that you can vote for certain blocks, or in this case, the term here is called a test. Yeah. Or you can also become a block proposer. So you have a bunch of validators. These validators, every 12 seconds, they would one of them would randomly chosen to become a block proposer. So when you become a block proposer, you can propose blocks to the network. So again, a block is basically a bunch of transactions. So when we say proposed block, it's nothing more than just this validator or you yourself, you are bundling a bunch of transactions into a block and submitting this block to the network, right? So once you submit the block to the network, you get attested by others. Attested by others means that, okay, people will check, or the other validators will check, is this block valid, or is this block legit? So let's say if everyone or more than or majority of the people or the validators think that, okay, this is legit, then they pass your block, then it will get included in the canonical chain, meaning the main chain, right? So yeah, this is a summary, but there's a lot of things that's going on behind the scenes, like fork choice rule, different things. How do you calculate the rewards and stuff like that? But let's not go into it because it's very complicated. So to summarize, this new consensus algorithm or proof of stake ensures that if you want to be malicious, if you want to make any false transaction, or you want to change the world state, you have to do it by risking your own money, because you are staking the 32 ETH here, right? But yeah, that's a summary of this. And okay, we are reaching the end, I think. Yeah, I think I already spent like almost 30 minutes. So let me just explain about the future of Ethereum. We have already covered the technical parts. So let's talk about the future. Wait, someone was okay. Yeah, I'm just looking at the comments. But yeah, let me just continue. So I'm just referencing from Vitalik's roadmap, and they have, I think, 6 or 5 roadmaps that is running on parallel. So let me just explain one by one. Right. So the first one is called the merge. So the merge is like what I said, has been done. It has been executed a few months ago, and I think they are still trying to improve it. But basically, the goal of the merge is to transition from proof of work consensus to proof of stake consensus, right? So yeah, I'm just gonna skip it. And the next one is called the search. So the search is also something that's very interesting. That will happen, I think, very soon. With this EIP 4844 implementation. So the search is basically trying to scale the entire network. So I think the current transaction per second for Ethereum is about 12 to 13 seconds per 12 to 13 transactions per second. If you were to compare it with traditional banking system or financial system like Visa or MasterCard, they have I think 100,000 transactions per second, right? So if you want to compete with those traditional Web2 system, if you want to onboard more people into this ecosystem, we want to scale up our network. So hence we have the search, right? And the most, I think the one of the most famous one, I mean the most talked about ones, or the latest trend is EIP 4844, Prudent sharding. Yeah. It's also very complicated. Maybe we have a session to talk about it later. I mean, in the future. Yeah, but yeah. Next, the Scorch. I don't know how to pronounce this. Scorch. Yeah, this one is I think more focused on MEV. So MEV, it basically stands for minor extractable value or maximum extractable value. It basically, to summarize, is to prevent validators from exploiting the user's transactions. Yeah, it's very hard to summarize MEV, but yeah, you can Google it and watch the videos yourself. But it's basically one of the it's a very important thing so that people don't get exploited. People like us, like normal users, won't get exploited, right? So yeah, this is the Scorch, I guess. And the next one, the Verge. The Verge basically is just referencing from here, verifying block should be very easy. This is more related to the storage of the entire networks, because if you have set up a full node on yourself or Ethereum node yourself, maybe Kevin we'll talk about the clients later. But if you have set up a node yourself before, the requirement to set up a node is very high, especially in terms of the storage. You will require about 2 TB of SSD storage, or to be safe, I think 4 TB, if not mistaken. So yeah, it's like 2 terabytes. It's very huge, right? So we want to basically reduce the storage requirement for for anyone to start their own node, and also to this also includes some cryptographic things, stacks, right, to facilitate all of this, right? Just gonna say it as that. Okay, next we have the Purge. This is more like sweeping up things. We have different things like EIP 4444, right? To help to simplify a protocol, eliminate certain technical debt, and also to simplify certain things that it shouldn't be so complicated. But yeah, you guys can explore about more of it if you guys want. Yeah, state expiry. This is also something that I'm doing in my own work. Yeah. Okay, the next one, the last one, the splurge, is to everything else. And one of the things that is in this roadmap is account abstraction, right? ARC 4337. So again, I think I'll be talking about account abstraction in the next upcoming few days, and it's a very exciting topic because, to summarize, account abstraction can help to improve the user's experience. So that's that, right? It's a very interesting thing, and for me, I'm very excited about it. So yeah, that's pretty much it about the Ethereum's roadmap. So let's go, Eve, and have fun, guys. Woohoo! Okay, yeah, that's all. Okay, so thank you. Ta-da! Okay.
Thank you so much, WeiHan, for a very, very interesting talk. I personally really enjoy it, and I hope everyone as well. We unfortunately, I don't think we have enough time for Q&A, but I think WeiHan will be around in the chat to answer your questions if you want. Moving on, we will thank you, WeiHan, by the way. Thank you so much. It was a great one. Moving on, we will have Kevin. Kevin, if you would you mind sharing your screen? And Kevin will talk about our next talk. A little bit about Kevin. Kevin, I forgot to introduce WeiHan just now. Both WeiHan and Kevin are community members of ETHKL, and they have also partake in many hackathons. And the reason why, like, WeiHan, I think I find WeiHan like a good person to speak is because he literally started from zero in the last half a year. He managed to even land a full-time job as a blockchain engineer, which is very inspiring. And now we will have Kevin, DevOps engineer, to talk about client-related stuff. I think he's the right guy to do it. So Kevin, take it away.
Okay, just give me a second. Okay, can you guys see my screen?
Yes, we can.
Okay. Yep. So thanks WeiHan for the nice talk, and also thanks Sichuan for the intro. So today we're going to talk about clients behind Ethereum featuring Sedge. So this is the content summary to just give a good idea of what we covered. So I'll be roughly going through nodes and clients, types of clients, some current mainnet statistics in Ethereum, why client diversity matters, and real-world examples of hacks and bugs, which are somewhat related to client diversity. Last but not least, we're featuring a tool from Nethermind called Sedge. So I was trying to find a nice high-level diagram. I found this from O'Reilly Media. I hope it just sort of paints the initial picture of what the network looks like. I'm pretty sure everyone knows that most blockchains, in this particular case, Ethereum, is a decentralized network. And you could just think of it as like a spider web. And within the spider web, you have a lot of nodes. There are different types of nodes and clients. They are like lightweight nodes, full nodes, archive nodes, and so on. So that gives you an initial idea of what we'll be covering. So nodes can be, even in Web 2 or traditional computing, it can be somewhat abstract term. In this case, it's any instance of Ethereum client that connects to the network. It's sort of like a computing unit, so to speak. Some of the terminologies that you may hear or see or read are full nodes, light nodes, and archive nodes. So you could probably guess from the name. So full nodes store the full blockchain data. However, they do occasionally do prune some of the data. Light nodes they just store some of the historical block headers, and then they will just sync all the recent transactions, which greatly reduces the storage requirements. Most nodes that, especially solos, validators, and node runners, they would opt to use light nodes simply because they can save money on having a 2 to 4 TB SSD. Last but not least, archive nodes just stores everything. Yeah. In terms of clients, you can basically spread them out in terms of execution layer and consensus layer. I won't go too deep into this because quoting from WeiHan, I could probably take a couple of hours just to explain this if I attempt it. But just to summarize, execution layer basically validates and broadcasts transactions, and the consensus layer, it bundles the transactions from the execution layer, EL, with the additional information and bundle up as beacon blocks. After this step, if you were to run a validator node, you would actually propose these bundled blocks. So I got this from the Ethereum.org website. So these are some of the execution clients. It may be very familiar to most of you, especially Geth, which is the current dominant execution client. Coming up next, we have Nethermind, Besu, Aragon, Aquila. At first glance, you can see that these languages are all in different programming languages. And there's a meaningful reason behind it. And you can see of course, the different networks and sync strategies that we just covered briefly. There's one called Snap, which I kind of missed out. Sorry about that. So consensus layer, which is formerly known as ETH2, because after the merge event, the consensus algorithm part of the which the node runs is split into like a different computing unit, so to speak. And these are the lesser known client names if you're not familiar with it. So we have Lighthouse, Lodestar, Nimbus, Prism, and Teku. As you can see, these are running on different languages as well, and they have their own respective networks which they support. So you may ask, why do we need different clients and how do they even work? So this is a simple high-level diagram which suggests that you have your beacon node here, which is aka a consensus layer, and your execution engine. So in the background, just to summarize, they actually do talk to each other, and they pass bundled transactions from, as I mentioned, from the execution layer to the consensus layer. And after that, it'll do its own thing and send out the bundle blocks to the network. So now that we have covered a rough idea of the different clients, I want to bring attention to some statistics. So I just pulled this out today. Of course, it may not be 100% accurate, but it's the best that we have, at least I have access to. You can see on my left, execution clients. So Geth is currently at 62%, followed by the Nethermind, Aragon, and Besu. And you can see that it's showing a red flashing symbol, which is not good. On the consensus client, it's somewhat healthier. As you can see, it's somewhat more balanced between first and second place. Of course, you may wonder, having such a large supermajority is what they would call it. Would it pose any issues? And this is why client diversity topic comes in. So diversity, when it comes to diversity, it applies to both execution layer and consensus layer. Imagine if Geth were to have any bugs, it would actually be a risk multiplier. That's why, as I've shown before, different teams and open source projects write in different languages to sort of even out the distribution. The actual goal is to have less than 33% of the market share for any given client in both execution and consensus layer. This is simply because the underlying code of the node, or rather Ethereum network, is written in a way where if any client goes above 33% dominance, and if any issues were to happen, it could result in slashing. Which is a way to impose penalty. That's just, of course, it's not always 32 ETH. There's some calculations that could be somewhat complex as well. Other risks also includes inactivity leak and rebuilding finality, which I won't be covering here today. So coming back to real examples, it's always good to have examples. In September of 2016, during a DEF CON held in Shanghai, there were a few exploits in the Geth client. Amongst the exploits was a denial of service attack, which actually slows down the disk IO, basically the read and write operations running in Geth clients. And this actually slows down proposing blocks for people who are running Geth. And thankfully, because of client diversity, during that time, parity was the second highest, having the second highest market share. So the network was able to continue because parity client was able to continue its own block proposal, which is of course essential to the network. But if Geth were to be super majority and inactivity leak would actually occur, basically it would start sort of imposing penalties and slash until the second largest majority kind of balances out the super majority. Another recent example is the Prism deposit root bug, Prism, which is one of the clients running under consensus layer. So this happened in April 2021. So just to summarize, this bug basically allows the Prism client to generate invalid deposits. And this also affects the Prism clients to produce blocks. And they actually sort of made them halt or not being able to produce valid blocks for up to 18 epochs. Thankfully, no validators were slashed, and there wasn't any gaps in it. However, the validators that are actually running Prism missed 2 or 3 attestations, which caused some minor rewards being missed out. Yeah. So as part of the client diversity preach, so it's good if you were running Geth or you know someone who's running Geth in for testnet, or if you were to somehow develop stuff on it, it's good to have this in mind and switch to lesser known clients. For example, as I've shown before, Nethermind is one of them. Of course, you can switch to some of the other languages as long as it's not the main majority today, which is Geth. And this is from the clientdiversity.org. It has a very nifty tool. You can just choose your current clients and tool B, and it will just suggest you a relevant documentation, which you can read up and see how you can switch over. So that's the gist of it in terms of theory. So I'm going to talk about Sedge. So Sedge is a tool developed by the Nethermind team, and they open sourced it. Basically, it's a one-click tool set up for the network and chain validators. Of course, if you were a developer or you were just curious, you can still run it. It's because if you're not doing validation, just like me, you can just run the execution layer and consensus layer, and you can probably hook up to graphs and whatnot. It's written in Go, so that makes it cross-platform because it can be compiled to the Windows, Linux, and Mac binaries. Of course, okay, all right. So what does it do? So I'm going to show you in a bit. So basically, Sedge is just a CLI tool, and it just based on your desired setup and mix of execution client and consensus client, it generates a Docker Compose script. If you're not familiar with Docker is basically a containerization technology, which makes it really lightweight for anyone from different OSs to run basically like little VMs. Yeah. Of course, fair warning, the tool is still in beta. Currently, it's at 0.6. So it's good to treat this as a test tool for now. So probably missed this one out. Let me just okay. So of course you would ask what are the testnet and mainnet requirements. Of course, mainnet would be much heavier, but I want to focus on testnet. So in testnet, basically most modern day laptops on desktops, you can probably run the testnet. For example, you need 300 GB of SSD, and I believe any basic internet would be sufficient. So it's really easy to run testnets. However, for mainnets, it really depends on the different clients. But at the bare minimum, you would need at least 2 TB. That's okay. So I'll show you how Sedge works in a bit, but when you run the tool, just run Sedge networks. You can see that the current supported networks includes Chiadu, which is a testnet for Gnosis. You have Gnosis, some custom network if you fancy. Of course, you have your Goerli and mainnet. If you were to run Sedge clients, it will spit out the different pairings and supported clients for different networks. So you can see your on your right, you have your Goerli, the mainnet, and these are the listed execution consensus and validated clients. Okay, so enough with all the talk. I'll just show you how easy it is to just get up and running. So right here, I'm just git cloning from the GitHub repo. So once that's done, just go into the folder and run make compile. So what that does is basically, depending on your whether you're running Windows or Linux or OS, it'll just compile the Go source files into an executable. And once that's done, I'll just change my directory to build, and you just run the executable. As you can see, you have a list of commands here, which I previously sort of hinted, which are clients, networks, and all the other more advanced or detailed commands. So next up, I'll show the running the CLI command. Before that, I'll just quickly go through some of the flags. So what I'm going to do now is I'm executing the CLI. I'm specifying my network to be, Chiadu, which is a testnet, because I don't have enough storage on my laptop. -C basically means that I want my consensus client to be Lighthouse and my execution layer to be Nethermind. And field recipient, it'll be used in some of the in the validator step. If you were to run the validator node, it's just your address of your wallet. So once you run this command, it'll just I'll go through some of the details in a bit, but basically it just generates your Docker Compose script. And as you can see, it'll say, hey, do you want to run the script and get everything started? Then once you say yes, it'll do its thing. It'll start pulling the respective privileges that you have designated, and you'll start creating your container. And that's really just it. I've highlighted in the video where you can see you have your consensus and execution containers, and these are the port mappings and some of the normal Docker information. So let me just pull up my terminal. So once it's running in the background, you can actually just check out the logs. It's going pretty quickly, but I'm just cancel it. But yeah, so what it's doing is the background, as you can see, is the execution client is basically syncing, and the order goes from when after your execution client is fully synced, your consensus client will kick off, and after that's done, depending if you want to run it as even as a test validator, your validator client will run, and hopefully that's easy enough to get everyone kickstarted, just to play around with, for free. You don't have to stick any real money on it. If you were to try staking even in testnet, I would recommend perhaps starting with Chiadu testnet, because it's, I believe last time I checked, it's 1/32 of testnet ETH, or in Chiadu's network, testnet Gnosis. Yeah. And okay, let me just cover this. Hope this is visible. So as I mentioned before, what Sedge actually does is just to create you can think of this as like instructions to run your respective Docker containers. So on my right, you can see that this runs a execution service. In my middle, it runs a consensus service. Or on my right, it runs a validator service. The actual file is quite long, but that's the nice thing about Sedge. It takes away all this complexity. You just tell it what you need, it'll generate it for you, and you just run it. I'm sure some of you may think, oh, do I have to run this every time I run my nodes? So the answer is no. This is just the initial setup. So let me just show you. What this is. I'll zoom in a bit. So this is the actual output from your Sedge CLI, if nothing goes wrong. And basically, you can just, all you need is really just this Docker Compose.yaml, and you can just run against this when you want to continue your, when you restart your laptop and computer. Because like I said, Sedge is like a one-time thing, unless you change any parameters related to your choices of execution clients or consensus clients. And coming back to the slide. So yeah, I hope that's at least you're wary of the tool for Sedge by Nethermind. You can always check out the documentation if you can find it. Yep. So they have documentation here if you want to read more into it. And there's the installation guides, which is very similar to what I mentioned, of course, in more detail. And feel free to contribute to the GitHub repo as well. Everything is open source, just in Go, which makes it somewhat easier than like Rust or Java and stuff like that. I think that's basically my the end of my. Of course, here are the references that I've used. Yeah, as you can see, and this is my Twitter. So yeah, that's it for me.
Thank you, Kevin. Right away, we already have a question. So the question is, can someone interact with the network if they host a light node, like using it with your wallet or custom RPC, etc.?
Oh yeah, definitely. So I mean, if you run a node yourself, as long as you expose the certain port mappings, let me just quickly show you. So if you look at these fields, right? I believe it's 8545. Yeah, that's it. So as long as you expose the respective port mappings for RPC, I believe this is the one, if I'm mistaken, you can interact with from the local and do what you need to do. Yeah. So yes, you can do that as long as your Docker container is configured correctly.
Nice. Thanks a lot, Kevin. I enjoyed the talk, and I hope everyone enjoyed as much as I do. We do have some time. I think Kevin, I think Kevin wouldn't mind taking more questions from the crowd. But if you're shy, you can always drop it down in the chat, and I will ask questions for you. I think WeiHan is still here, so questions for both of them are fine as well. And if we have no questions, I will like to tease a bit about our next event. If I only can share my screen. If I can only find out which one to share. So I've already created all of our confirmed online talks on Meetup, and I will share those real soon on Telegram, on the IFKL Discord Telegram group, and also on the KL Mini Hackathon Discord group. Do check them out. The next one will be on the 14th of February, 9 p.m. By WeiHan again. He's going to talk about account extraction simplified. So remember, just now among the audience, there was a little discussion about account extraction. So that is where that is when you want to go for it, go to understand and learn more about account extraction. And of course, you can discuss about that during the session. And right after that, it's going to be another back-to-back talk at 9:30 p.m. It's going to be by me. Introduction to Starknet. So Starknet is a layer 2 scaling solution on Ethereum. So for those who are also asking about how do we scale, like there was a TPS related question. Starknet offers one of the solutions to that. So two very exciting talks on February 14. And on February 15, we have a Cairo talk by Wen Kang. Cairo is a language on Starknet, and we will walk through why Cairo is important and what is so special about Cairo. And on 16th of February, this is going to be on 10 a.m. because of time zone issues. We invite Scroll. Scroll is another alternative to Starknet and whatever L2 scaling solutions out there. So they are running using a ZK EVM method to perform scaling. So again, TPS questions, this is another one that you want to check it out. Back to the questions. By Sri Putra. What is the advantage of using RPC to send transactions, retrieve data via own node versus providers? For example, Alchemy and Infura.
Yeah, I'll try to chime in on this. So you can imagine where sometimes, for example, the default RPC provider in MetaMask is Infura. And of course, you can imagine if everyone were to use the same endpoint, you would be somewhat competing with the other requesters. And sometimes if you want really fast submission of transactions, you could possibly think of using your own node or maybe like a hosted node with some of the cloud services. So that's one of the main motivation most would use that. And of course, there are more like topics about like censoring certain transactions from certain addresses, which we'll probably not go into. So that's another thing to think about. Yeah, at least that's my understanding.
Yeah, just let me chime in on that. Kevin has touched on censoring because Ethereum is a public blockchain that aims to be transparent. So if you were to rely on Infura can possibly reject your transaction and not include your transaction into the block. So that's the risk that you may face. So by having your own node, you're guaranteed that this won't happen. There are also many complicated stuff such as like MVV, you get your transactions fund run and stuff like that. But again, this is a very another topic for another day. Perhaps we can invite more speakers to share about those. Or perhaps Kevin can share about those in the future. Okay, this is a long one. I have one question that's regarding the encryption standard of Ethereum. Since quantum computing is getting much more powerful over time, all standard cryptography needs to be swapped onto a more quantum-resistant cryptography in the future. Hence, my question is, whether migration to use another type of encryption method on Ethereum hard? If it's hard, how long of the duration do you think it can be completed? Sorry for the long question. I think I'll take that. I think that's a very good question, and that is behind everyone's mind. But I've been following a couple of like podcasts and a couple of people sharing their ideas on this, views on this. Quantum computing is getting much more powerful over time, but for it to be able to crack like a Kerchak 256 algorithm, it will take around probably another 50 to 100 years. So it seems that everyone is not that anxious. And again, this is another strength of Ethereum because the developer community is always building, always looking out for the latest technologies or vulnerabilities, as compared to Bitcoin developers who are happy by not with the stability that they have. Ethereum devs are much more eager to adopt and change. So yes, this is something that will happen. And if I'm not mistaken, and with account traction, swapping out the hashing algorithm will not be too difficult but there will be backwards compatibility that we need to think about. So it's tricky, but not impossible. It's a too long don't read answer. All right. Excellent. Right. So thank you everyone for
participating.
Hi, yes.
Sorry. I'm Han here.
Hello.
Hello. Hopefully it's not our topic, but perhaps you can like share your experience, your previous experience on like hackathons and stuff like that, how you get ideas and stuff like that. Hopefully it's not our topic. Since we're in a mini workshop.
This is a great topic. But before that, let me answer another topic. Please bear with me. Another question. There's someone. Okay, bear with me, Han. What if we have a breakthrough in algorithms cause of uncertain? Now the best algorithm we have is against Grover's algorithm. What if something as powerful as Shaw's algo against RSA come out in a few years? That's a good question. Unfortunately, Nicholas, I'm not able to answer you. But I'm able to point you to the right direction. There is a group called Ethereum ETH R&D in the Discord group. That's where the core devs are constantly discussing about the latest protocol designs, the latest protocol change. But yes, this is a very good question. I'm not cryptographically sound or cryptographically knowledgeable to answer that. So yeah, apologies for not being able to answer your question. Yep, you're welcome. So Han, yes. Okay, so back to your question about hackathon ideas and experience. So again, this let me stress the goal of this hackathon. The goal of this hackathon is for everyone to get hands-on experience on building their first Web3 applications or for the first time. But of course, it's open for everyone, so feel free to join. We don't expect you to come up with like super fancy innovative ideas because this is only a small scale hackathon. But if you have, just go for it. Ideas, we do have a couple of ideas. There is one idea that that came out that people have thought of but no one is building. Probably I can drop them down in the Telegram later, so that could help. But how do we generate ideas? Normally, we just have to, how can I say, that's a good question, to be honest. How do I come up with ideas? Normally I can't I don't know how I generate ideas. It just comes by naturally, and we bounce ideas among our friends or participants. So we try to probably solve or tackle on current problems, such as, for example, if you think that the wallet UX is horrible, we try to come up with a better wallet design, and such is why account extraction is strong, and account extraction is also one of the recommended topics. So if you're able to come up with a nice wallet UX, that could be a very good idea. And we also look at recent trends, like what are people building on, like ZK is zero knowledge is also something that people are building on. How do you use zero knowledge technology to implement privacy on the public blockchain? So that is something that you could be looking at. And previously, executions are expensive actually it is still now on layer 1, but with the advent of layer 2, executions are much cheaper. So it opens the doors to a lot of heavy gas, expensive, which are previously impossible applications or protocols, and now you are able to do it on L2. So that are also things that you can look into. Or some L2s will need infrastructures that are not existing on the L2s. One common example that many one has is the name service. I think everyone used to create like a name service for hackathon, and we'll definitely get something. Like recently I saw that this Filecoin name service, which is just like, forgive me if I'm being a bit too harsh on this, copy and paste from the Ethereum name service, and they got, I think they made it to a finalist. So not to suggest you to copy and paste name service, but probably you can look into what infrastructures or applications that are available on layer 1 like mainnet, but not available on a particular chain like Scroll or Stucknet, because they are two of our sponsors. That's why I'm highlighting them. But yeah, I think these are how we come up with ideas, and I hope that's helpful. And feel free to unmute yourself again should you want to ask more.
Oh, I think that's a very good overview of what to expect and stuff like that. Thank you so much. Thank you so much.
You're welcome. I hope you enjoy the week, and hope everyone enjoys hacking and building and learning. That's the most important.
Thanks once again. Thanks to WeiHan and Kevin as well, and to Chi, to you as well. Thanks.
Yes, thanks. Yes, for sure. Thanks for the speaker, and thanks for audience for listening, tuning in. Your support means a lot to us. Oh yeah, we got another question. I want to execute transactions on layer 1, such as updating on state stain, but I want to do it bulk and cheaper. Can I use L2? So this is a question that will require a long answer. I'll do that. The thing about layer 2 is that they are not directly interconnected, so to say. What layer 2 does is that they updates like the state. They perform some transactions, and then they will publish like the state change on layer 1, and with a proof, depending on if you're optimistic or validity rollups, they'll update like a proof saying that the state change is correct. So you can think of layer 2 as a blockchain of its own that relies on layer 1 for data availability, and for the how can I say, the finality, not finality, but the validity of the state change. I forgot the word. Yeah, I hope that answers the question. iPhone asks, is there a recording for this? The answer, yes, it will be recorded and uploaded to YouTube as soon as possible. All right, I don't see any more questions. And again, I encourage everyone to highly utilize the KL Mini Hackathon Telegram group to look for teams, bounce ideas, and ask questions regarding the events, regarding the workshops, or yeah, whatever you have, post it there, and a couple of us will go there check regularly. So to help you and to make sure that you enjoy the entire week. And do not stress out if you do not come up with a brilliant idea, because number 1, it's free. Number 2, it's all for fun. Number 3, learning is the most important. And again, thank you so much, and looking forward to all your submissions, as Kevin says. And I will see you on the 14th of February online. So everyone, bye-bye. Have a good one.